out there. Now, I didn't have to do anything over at the... Crap. Here, I'm going to share screen real quick.
Okay. All right, I'm just going to check that it's...
Yeah, you check if we're streaming. If we are, everybody, we apologize. We have to invent this.
Yeah, it's still on YouTube here. It still says scheduled. So it's not live yet.
Okay, good.
Are you... So in XSplit, you've got it hooked up and going there?
Yeah. Okay, so there's the website.
Error, duplicate stream key.
Oh, I couldn't even read that. That's what, right, because I'm viewers waiting 3.
Okay, so now in XSplit.
Do you see XSplit?
No, I see your YouTube browser.
All right, let me do it again.
Someone says I see and hear you both.
Oh,
Linus.
Wow.
Cool. For some reason, I'm not.
Thank you. Well, then, hello, YouTube. We should ask that all along. We're having trouble with the YouTube settings, and I don't know about you, Ben. I hate YouTube settings.
I'm going to have to go back to my LinkedIn and edit this.
So today we're going to talk a little bit more about PC boards, maybe some software. We're going to pick up on where we left off and show some of the images that we talked about last time. And Ben, I've already forgotten. Oh, you're checking us out on YouTube itself?
Yeah, I'm just making sure
Okay.
Because I posted to LinkedIn and I needed to make sure it was the correct stream link.
Well, the good news is now you're in both channels because we were doing a share screen earlier, I think.
Now it says, it's weird. On one tab, I've got YouTube and it's actually playing.
Okay.
But on the other...
So it's like I started 2 transmissions, maybe.
Yeah, on the other, it's waiting.
Yeah. We should probably have a guest host that actually knows how to use YouTube and XSplit both together. I'm not saying we don't, but I did something wrong. All right, moving on. So last week we were talking about this cute little triangle generator, which we made with a PIC 16F. And one of the things we can try and show today is how I programmed it, but we were having trouble with that a little bit ago. Yes, you might say, you guys have trouble with computers? Yes.
We do.
The easy things are hard and the hard things are easy.
That's how it all goes. Okay, I'm not going to look at that now. I know it's running, so
all right.
Let's just talk. So,
yeah.
Today, Bill, what are we talking about?
Yep. Well, actually, I wanted to show the Hackaday article I did on PCB construction because we outlined it. Can you show that in your share screen? Mine broke.
Let me bring up a browser.
So if you Google high speed, and this is for everybody, if they Google high speed PCB Hackaday or Bill Hurd.
All right, so yeah, Bill Hurd, you come up. It's wonderful. Let me share screen.
And I got mine to work too. So let's go with your screen first, though.
So Hackaday, high-speed PCB. And there's a bunch of videos you've done here about high speed. You're holding up one of my favorite books there.
Oh yeah. But yeah, I don't know why mine didn't come up, the one I was talking about. You know what? I got mine working. Let's try mine.
Yeah, switch to you. Yep.
All right. And it just broke. Jesus Christ. Excuse my language. All right. Come here, you. And scene 10? No. Ooh, cool. Wrong one. I should just have those sprinkled throughout.
Yeah, why not? But we need to do a sound effect that goes with it, like a swoosh or something. I don't know.
Oh, you're not hearing the swoosh?
No. I'm seeing
there's a swoosh.
I'm seeing your, there it is. I'm seeing your Hackaday page there. So if people want to find this, they go to hackaday.com or is it hackaday.io?
And the name of the article is Putting High-Speed PCB Design to the Test. Now, that's the title's written by the editor. But this is all the things we talked about last week. And there I'm even showing an old two-sided board where it shouldn't have been two-sided, but there was no way we could afford to make that a four-sided board back in the 80s. So we just didn't do impedance control. We ignored it and did series termination resistors. So we knew we were sinning, but we went ahead and tried to absorb the reflection with anything from 22 ohms to 68 ohms.
And we still do that.
Yes, we do. Because we can't always.
And Bill, something I never understood. In my early days in this industry. Okay, so here's and Bill, you never went to university for electronics, but I classify you as one of the greatest electrical engineers in the world. And so I'll preface what I'm about to say by saying that you don't need a formal education to learn all this stuff. You don't need to necessarily go to school for 4 years. And in fact, a lot of engineering universities will give you 4 years of theory.
Okay, we just lost Ben. Hopefully he comes back. Oh, we lost Ben there for a second. So I'll start talking. You keep talking. There you are.
Yeah. Did it drop out?
It did. So you were saying 4-year university.
I think we're back. I was saying that I wanted to make a comment, but I wanted to preface it with you don't have to go to a 4-year electrical engineering degree to become a great electrical engineer. You can be an autodidact like Jerry Ellsworth or yourself, Bill. Some of the greatest
and I
engineers
just watched
in the world.
a guy. Yeah, I just watched a guy named Mike Fikes pick up like 3/4 of what I know in like 3 months, but he's an unusual person.
Right. So my point is, I'm not dissing people who don't go to university. But I will share a comment from my own experience related to signal integrity and how signals actually go on printed circuit boards. I went to college first and did an associate's degree and then worked in industry for at least 10 years and did all sorts of different jobs. I did IT work, I did network engineering type stuff.
Yeah, things like that, which is means there.
IT service and support, because those jobs paid better than electronics technician jobs did. When I started, I was an electronics technician repairing stuff at
same here
level.
Yeah, I was a production tech. That's how I started.
And I would design boards, and I knew nothing about signal integrity, absolutely nothing. And then years later, I went back to university and actually did an engineering degree, and I knew I didn't have to. I did it because I wanted the pressure of having to do assignments in a given time frame to force myself to learn things. But all that work experience before that gave me the context under which, or on top of which, the theory actually made a lot of sense. But there were other people studying straight out of high school, the same degree program, and they were good at the mathematics, but they just struggled with the concepts because they couldn't really see clearly why and how they would
field.
Be applied.
They probably couldn't see a field, and probably had been taught about electrons. You know, you and me learn that batteries are backwards, and it's not all about electrons, right? It's about fields and things like that.
So when I So when I got into high-speed designing and return paths and maintaining a good layer stack up and all of that, it just it didn't make sense until many years later, after I'd done both, you know, practical experience plus the electronics engineering degree sort of level training on top of that. But I just want to say you don't need that to learn this stuff. There's some really good books, and there's a lot of articles like this one that you wrote. It's enough to be a really good PCB designer to absorb this kind of information.
Right.
You're getting a cat from me for some reason.
Yeah, I just saw that. It looked like a screensaver. So
I don't know why. Yeah,
I backfilled my math afterwards. So my math was real poor. So I used placeholders, and I wrote programs in BASIC to do the math. I couldn't do Laplace transforms because somebody had used the phrase imaginary numbers. And I'm like, what do you mean? They're like square root of -2. And I thought they meant that one value covered all imaginary numbers, and you plugged it in and you imagined it. Well, no, they're just talking about an equation that doesn't exist with real numbers, but Euler, you know, it had an equation where the answer is the square root of -2. So if somebody had just said the frequency dependent component, I'd have gotten it 20, 25, 30 years ago. If we had the real component and then the frequency dependent component, which has L's and C's in it. And of course I know they're frequency dependent. There are L's and C's in it, right?
Actually, well, that's a great point, Bill. I personally have a very strong feeling that, or opinion, that mathematics teachers, even in senior high school, when they start in the advanced mathematics classes, they start talking about imaginary numbers. They take it from the first time you learn imaginary numbers, whether it be high school or at university level, you're being taught by pure mathematicians, not by engineers who know an actual practical application of it and why it's needed. If the curriculum could be redeveloped to show first an application. Okay, so you have a coil that's part of a suspension on a motor vehicle. By the time you're 14, everybody has seen that and understands what it is.
Right.
Okay, what happens?
And understands what it is when it wears out.
Yeah. What happens if you have a spring and you hit it? It vibrates, right?
Right.
So there's this. You start there and actually introduce imaginary numbers as a way of modeling some of these real world things, versus the other way around of saying, oh, there's this thing called I or J, depending on what.
Right.
And imaginary is actually also a dumb term. Complex numbers.
It's totally stupid.
Because they're not really imaginary. They're just complex. So I prefer complex numbers.
Yes, and complex to me means the real part and the frequency dependent part. Once you put the two together, it's real.
Yes.
Yep. Hey, you talk about oscillations. Here's how I learned oscillations and energy, and you talk about that vibration of a spring. This is a grid dip meter, which is basically a tunable C and an L, which I can put on here, a coil. And I have a whole selection of coils. And I went around testing everything. I'd see what frequencies it absorb. You can put this up to a coil and figure out the value of the coil or the tank circuit next to it by tuning and watching the meter dip. It's a grid dip meter. That. I was doing it to the cat, you know, to little circuits. I would take a circuit like this and I would sit there and probe it while it was powered up. And so you know.
So what's the resonant frequency of a human?
We mostly absorb. That's what I learned from the cat.
I know. So, I'm just a bunch of jello right now.
So, hey, you mentioned ways to learn and favorite books earlier. There's one of mine, Henry Ott's.
Oh, I've heard of Ott. I don't have his book. Yes, that one I have. That's expensive, but worth getting if anyone's designing PCBs.
And Dr. Johnson has retired, but he's still spoken with reverence.
Dr. Johnson retired on that book and his trainings. He made a lot of money because he
they all do, I think.
He demystified signal integrity right at the right time in industry. So now there's YouTube and there's a lot of people like you and me who do understand this stuff, have read his books and other books and have the experience.
Hey, are we streaming on the right channel? Are we streaming on Bill Hurd with no space? Because I'm on that channel and I don't see anything. I see one person waiting.
As far as I can tell.
Okay. Hey, so here's another book. Do you remember this one?
Yeah, we're streaming correctly.
Oh, excellent. Yes, you are. You're live. Okay, thanks, everybody. It got so quiet, we wondered. So here's one for you. And this, you wouldn't think that this is a way to learn something because it's about MECL, which is Motorola's ECL, emitter coupled logic. But everything's in here. There is a couple mistakes, but the trick is get so good that you find the mistakes. And they show about terminations, everything we talk about. This is a book from the 70s.
Okay, so that you said termination, and that brought my brain back to what I was thinking of when I started waxing lyrical about university degrees and whatnot. Is termination is one of those things that even at the associates level, when I was learning to be a tech, they did explain it. They said, and we did a basic transmission lines class. We had huge coils of low loss coax, right?
Right.
And we'd actually, measure them with oscilloscopes. We'd do TDR stuff, but we did it with actual oscilloscopes and pulse generators. So we knew how a TDR works.
TDR is time domain reflectometer, which tells us how long it takes for a signal to come down and back.
Yeah. So essentially we learned, how to tell if you have an open circuit and roughly how far down the line it was. We learned how to tell if you had a short circuit and where it was. We learned that you had to use the right value of terminator.
Right.
But here's the funny thing was that all made perfect sense, and we did the math, and it was kind of fun. But the terminator was always a load between the signal line and ground, which you call parallel termination.
Half of a parallel termination. And true parallel has a signal to VCC and to ground.
Yeah, right. So that's another
it's a
way
load.
To do it. But if you have an unbalanced single-ended line, you put a load on the end that's matched. And then with digital electronics designing PCBs, there was never any termination because we were going at low speeds, right? And
lower power. And we didn't want to throw it away in a termination.
And we loved CMOS because the inputs to all the gates were practically open circuit, so they didn't present any real load other than a little bit of capacitance.
But they're bad then because they'll reflect the entire signal because they're high impedance.
Right, and then the teachers at college said, well, we actually want that because that's what drives the voltage. That's what drives the voltage all the way up to VCC when a signal goes onto a digital net. But the problem now is, once we started going up around 10 megahertz and higher in our signaling, then reflection started becoming a problem. We'd get all this ringing and all that.
Right.
And what no one was ever able to explain to me clearly at that time was why we have series versus parallel termination.
Right.
And in a lot
Ring.
of high speed, yeah. So high speed, high Z input calling. I like that. Thanks, Chris. So
yeah, shout out to Lord Megatron. So yeah, you were saying why we need the series now and the
series versus parallel.
Right. Right.
To stop reflection.
So what do we mean when we say high speed though? We don't mean you can have a 1 megahertz signal and have a 50 megahertz component, right?
That's right. And that's exactly what your article's talking about there in that quadrant. You've got, because you've got high edge rates, you've got a lot of high frequency content in that. And anyone who's done, Fourier analysis, so at some point in engineering, you get into looking at the frequency content of every signal. And those fast edges happen because silicon switches very quickly now. We also want, most of the time we want fast edges.
Right.
Because that allows.
We want them to get there, but we want them to then die down quick. We don't want them hanging around for the next 6 nanoseconds.
Right. So and that comes back to the termination. You need a critically damped system.
Right.
And the series termination versus parallel, you could do parallel termination, but the series termination, if you look at an input gate on CMOS, it's still a capacitance, but to those high frequencies, the capacitance appears as, at the higher the frequency, the lower the impedance of the capacitor.
Right, right.
So to those high frequency harmonics, the input gate of a MOSFET appears like a short circuit. And so the series,
different frequencies, yes.
The series termination is just a current mode way of controlling that termination. So, and Chris, you're saying it's amazing how we have to implement special controlled rise time transceivers. Yeah, it's true. I mean, we're
really spoiled in our FPGAs and stuff. We just slow them down. It's when we go back to the older stuff that we have to start watching our edges again sometimes.
Well, or even discrete. And occasionally we still want to use one of those tiny little, single or dual inverter gates.
They become real popular. Yeah, the 1Gs and stuff.
Yeah, we still need a little glue logic here and there, or some
jelly beans.
Yeah, popcorn components, right?
Yeah, yeah.
You still, that dies on those. So this is something Rick Hartley talks about that I really enjoyed, was an existing product in the market for years, no problem, passed EMI, FCC certified, then the Texas Instruments or whoever it was that made some of the logic chips
changed them,
did a die shrink. I said, it's a drop in. It's exactly the same part number, same order number. Suddenly, this company's product were failing EMI testing.
Too fast. Yes, too fast, probably.
It all got too fast. The die shrink actually increases the speed of the output drivers, and that creates noise. Created noise and ringing. Failed EMI testing.
Fast isn't always good. Sometimes you can get on a data bus too fast. But in the old days, I used to like LS because compared to AS or F, you were asking for trouble if you used one of those. And I have put an F part into production, but it was because nothing else would do. But yeah, you want to use the slowest family that works is a good rule of thumb.
So if anyone's watching or listening who is not aware, there's different standardized logic families developed by the industry, and they're standardized by IEEE and JEDEC, and that's what Bill's referring to. LS, Well,
we could do a whole episode on that.
We could. It all started back in the 70s with the 7400 transistor logic, TTL.
Yes.
TTL, transistor to transistor logic, is what that stands for. And they were slow 70s technology. Then 80s they came out with, or late 70s came out with LS, which stands for low power Schottky transistors. So they used a different, and then advanced Schottky, and then ALS, advanced low power Schottky, and then they came out with all sorts of this. Tons of them now, like ABT,
ACTs, yes.
Yeah, and then CMOS came out with C, and then HC, high-speed CMOS, which is really not that high speed. HC.
No, they were dogs. They were horrible. You didn't use them unless you were battery powered.
Yeah. Or interestingly enough, the original CMOS logics were all those 4000s, and the 4000 series. They were slow as dogs and horrible, but they had this one beautiful thing about them, was that they could all operate from like between 3 volt to 12 volt VCC, or even 16 volt in some cases.
And you could use them as MOSFET arrays too, like the 4016 and stuff. There were ways to get to the parts inside the CDs.
Yeah. Yeah, I remember that. There are some actual guitar overdrive and fuzz pedals that use...
There you go.
They use the 4049 as a high gain amplifier. That's just.
I
really
did ultrasonics
distorted.
using a 4001 with a 10 meg feedback, which held the CMOS part right at half VCC.
Yeah.
And then I put an ultrasonic transducer in it, which has nothing for current, and it worked. I was able to power out thing, and gain was like 10,000, something like that.
It's a poor man's high gain op amp.
Yeah. 4046 phase lock loop.
Yeah.
My favorite phase lock loop in the world.
It
saved my life. It threw itself in front of a raging car one time, pushed me aside, saved my life. So it's my favorite phase lock loop. That's for sure. Actually the 128, we had an 80 column chip. It was 1 week before CES. And the 80 column chip was trying to work asynchronously, and they didn't try and synchronize it with flip-flops. And I asked the guy, so why didn't you try and synchronize, which means to keep clocking it until it's clean? And he goes, well, statistically, even a certain number of these stages will still fail. But it's like one every 300 years instead of once a second. And so I had to make the show, we used a 4046 phase lock loop in a little tower that sometimes I have laying around. And made it so it ran off the same frequency as the VIC chip, the 40 column chip. So so those old CD 4000 series, they're still, they haven't obsoleted them, strangely enough.
Yeah.
So so we talked last week about the weave.
Yes, we did.
Whoops, I did it again. Where'd it go? All right, we're going to do the weave on this one. Hang on a second. Screen capture, smart selection, boink.
There it is.
And now we'll make it big. And here we're showing the fiber from last week. Ben, you want to talk about the difference between those two orange lines that represent the copper lines right here and here?
Yeah. So one is has that huge long section where the copper is mostly over a high decay. So the glass weave reinforcement within FR4 printed circuit board material is what you're looking at. And
yep.
If you have a differential pair and one trace happens to be routed over where there happens to be more glass, that has a higher dielectric constant and therefore higher capacitance, and that and therefore lower
That'll
speed.
slow it down. It'll desynchronize it. It'll change the load on it. But mostly it's the propagation speed will change, right?
Yeah, so that will delay, and really you want those two signals to be traveling together the whole way down the differential pair.
Differential's not so much about canceling the voltage on both. In fact, the noise on both, if it happens right when they're crossing, and you may have seen cats, and I know you have been, but I'm referring to
the
everybody
eyes.
else.
Eye
The eyes,
diagrams.
yeah, I call them cat's eyes for some reason from the old tubes. But they're really, we're making edge detectors, and we want both edges to be the same. If one goes high at one time and the other one goes low, that's noisy, but if we can get them both to cross right at the same time. So there's a theory that says, well, we don't want them both to have noise at the same time. We'd rather have just one be noisy and then have the other one be noisy randomly. And so there's a school of thought that says run your differential traces differently rather than next to each other, as long as they're the same length.
Yeah, and
now, would I do that? No, I would run them next to each other because I'm not going to take a chance. Yeah.
The theory though is common mode noise. Common mode noise is easy to reject because the receiver is only looking at the difference between them. That's why they're called differential pair. But the problem with on PCBs and chips is it's kind of a moot point because the receivers are really two separate MOSFET gate inputs usually, and if noise on a high level, say, is on the trace, it can actually push the voltage up to where it's shorting out the clamp diodes on the input.
Right.
So
right.
And
ringing, if you count the time that a signal is valid, let me back up here a little bit. If this signal comes up here and then rings for 10 nanoseconds, guess what? That's 10 nanoseconds off the top. You don't count when it overshoots, and you don't count when it undershoots. So a ringing signal's slower than a signal that doesn't ring for the logic. Hey, somebody mentioned 45 degrees. Let's talk about that again, because, and I'll find it in this, but somebody mentioned 45 degrees. We used to say 17 degrees, right, or 11?
Yeah, the other way to mitigate that fiber weave effect is, yeah, exactly what you've got there. You ask the manufacturer to tilt the board on the panel 12 or whatever degrees. It costs a lot more because you're wasting panel space.
And you could still accidentally get two different impedances. It's an averaging technique, but at best.
Yeah. These days I wouldn't do this. This was what we did before spread glasses were available, but now it's not too expensive. It's actually cheaper to use to specify a spread glass, like that 7628 you've got showing there. Scroll down a little there, Bill. You've got the 7628 weave. That's a spread glass, and you can also get a 1086 spread glass, and you don't need to be that prescriptive. Usually the PCB fab will tell you what they've got on hand that's going to work for good signal integrity. You just tell them, hey, this is high speed. We want spread glass, and they'll figure out which one to use usually.
I was going to say, yeah, it always helps to ask the PC board house, because if I show up with, going, oh, I want this fancy weave, and they may go, one, you don't need it. Two, we use tons of this other stuff, so it's cheaper and even maybe better.
Yeah.
So, yeah, I always ask the house, the PCB fab.
Be practical and realistic. If you're talking about differential pairs that are dealing with signal rates, that are in the hundreds of megahertz, you just specify good material, and you probably don't. The amount of difference and skew between them is not going to be enough to be a major problem unless you're going a huge distance. But if you're up in a modern sort of DDR4 or whatever, and you're doing, you really need that signal integrity to be much better, and your clocks differential signal that over a gigahertz, then yeah, it matters.
Look at the difference right here. This and I actually did this with my own. I have a CSA here, a communication signal analyzer.
Mm-hmm.
And it's got a resolution of about 10 picoseconds. I mean, and the horizontal trace, you can see it's right on the 50, the orange line, and the vertical trace. Now, I changed the divisions by accident, but you can see the vertical trace is off by almost 10%, at least 5%. And so now that was a cheap board. It absolutely was a cheap board because I didn't think I'd see the difference, but it sure did show up the difference. So now this is a TDR. Do you want to explain TDRs?
A TDR is just really a special application of an oscilloscope. You send a very how do you say it?
Quick, very fast,
sharp,
high rise time.
Yeah, an extremely sharp as you can get it, pulse down a transmission line, and you're measuring with an oscilloscope the front end of that transmission line where the pulse goes, and it reflects. Any reflections come back up the line, and you see those reflections add to the waveform that you're measuring at the input end. And so as time goes on, those reflections take time to get back. So if they add or cancel out, that's what you're looking at on the waveform. I'm probably not explaining it very well.
No, that's fine. So how fast does it travel on a PC board in typical?
It depends on the dielectric, but if you're
the FR4
standard
dielectric,
FR4,
yeah, it's about six nanoseconds to or I'm 6 inches to a nanosecond,
or something like 6 inches to a nanosecond.
Hey, I'm going to do a shameless plug for somebody I met online. This is a device called a Pulsar by Leo Bodner, leobodner.com.
Yeah,
and what
I've
happened?
seen that.
Yeah, this is like a 10 nanosecond. I mean, he gives you the actual rise time of your unit, and mine was like 12 nanoseconds or something. This costs $50, maybe 60, 70. Well, other people are charging thousands for this, and I went to build one before I found Leo's, and I was going to do a Hackaday video on all the different ways, avalanche diodes and stuff. Once I found Leo's, it just became go buy Leo's.
Yeah,
I just know, and he used a laser driver, and you can picture that these things are meant to go gigahertz on and off and on, and so that's why he got it to work, as he used the right components to begin with.
Yeah.
So
because that's all about slew rate.
And you can control this. You can control things. It's got a USB port. So, and he's got a little app, and you can change things like the delay or maybe the rise time.
That's awesome.
Yeah. So shameless plug there.
But what else do you need besides the pulsar? You need a very high bandwidth oscilloscope to go with it.
Yeah. Now my CSA
that's where the money really is.
You want to guess the bandwidth on my CSA that I bought used off eBay?
First of all, how much did you get it for?
$500.
That's insanely cheap for something with that.
It's insanely cheap. It's a 50 gigahertz scope. And the TDR module's 20 gigahertz, but the scope itself is 50 gigahertz, which is what, 2 picoseconds, something like that.
How did you get that for $500? That's crazy.
eBay CSA 803. Now a friend of mine, he got bit by the bug once I showed him this, and he went for an 8300, and he paid more, but it has an Ethernet port and everything. This thing's 20 years old, but still does picoseconds, right? So yeah, check it.
How did they do that back then, Bill?
Oh, it's amazing. If you look in there, and Leo's fixed a couple himself. If you look in there, the connector is part of is a component. The piece of wire from the connector has a known inductance. It's the only way they could do it is every part is part of the circuit, even if it's just a wire. And there's only like 5 parts, and there's no ESD protection. This is the one thing, when I use that piece of equipment, I'll actually put on a strap, because if I blow it up, there's no ESD protection that'll go 50 gigahertz, at least back then. So there's no protection on these things. So that have you ever blown up a spectrum analyzer by giving it too much?
No.
I bought one off eBay, and I think the person before me did. I now have a nice Tektronix, but I bought a spectrum analyzer off eBay, and it was dead. I mean, the input was never reflected. Yeah. So what else is in this thing? This turned out to be a good article. I enjoyed writing. Oh, when I wrote this, I went to the Altium event 2 years ago, and came back and wrote this because I was so in the moment of PC boards, you know, and I listened to Lee Ritchie talk all day, and then like people like Rick and stuff. Oh, and Eric Bogatin was talking about, you know, the actual formulas.
Corners. Yeah.
Right.
Yeah.
So the thing about right angle corners, people go, and I saw somebody do this to Lamore from Adafruit. They're like, oh, you used right angle corners on your IO lines. Guys, it doesn't matter on your IO lines.
Now for digital, it's only something you care about for RF, where you're not actually dealing with pulse type waveforms. You're dealing with modulated sine waves, and any reflection is lost and you can use these structures deliberately to actually create transmission line filters and things like that. But if you have to be intentional with everything you do with RF board design. So
but at regular frequencies, even, and by that I mean, let's say below a gigahertz, right? Sure, the corner represents, if you had a square corner, it's like this extra triangle here I'm trying to show glued onto it. Well, yeah, that's a change of impedance. It's a little extra capacitance. But the thing is, it goes by so fast, sub-picosecond to the signal traveling by, that it goes bump, and that's it. It's just so small, it doesn't matter.
Well, and beyond
that, what matters more is vias.
Yeah, beyond that, no CAD tool actually makes square corners like that anyway. They're all based on routing the board with a round shape.
Oh,
aperture.
Good point. Yeah, that's the days of, we used to do laser apertures, and you would definitely see the laser radius in there.
Yeah.
So tell us about vias, why they blow. I'm trying not to say suck.
But you just said it.
I know, it's YouTube. I'm allowed.
Well, vias are a completely different shape. And there's all sorts of different models for vias. They have a lot of extra capacitance, but they're also, you're changing layers, and so you're changing the shape of your transmission line. You might be going from a microstrip to an embedded microstrip, or from a microstrip to an offset strip line. And you can plan your trace widths to maintain an impedance, but the via is the same size all the way through. So it is also an anomaly, and this is why in the original PCI spec, not even PCIe, I'm going way back to the 90s when PCI came out, 33 and 66 megahertz parallel PCI bus on computer motherboards. The first rev of that spec, all the boards were still through-hole pretty much for the connectors. In fact, even today, PCIe, most motherboards still have through-hole connectors, and there's ways of mitigating signal integrity and reducing reflections even with through-hole connectors. But we were only talking about a 66 megahertz clocked bus, which is pedestrian by today's standards, right?
Yeah.
And they specified in the PCI bus specification for physical, they limited the maximum trace width, but they also limited the number of vias on your PCI bus signal to no more than 2 vias. But and that's
a good rule of thumb, anyways. For if you're using more than 2 vias, you better know what you're doing. Is kind of the way I look at it.
Well, what they didn't understand was can actually, for high speed, a lot of the reflections were caused, and this is why vias cause problems for people. You change layers and you think it's fine. Okay, no problem. But every trace, if you go back up to your image you had there with the blue colored pictures, the vias, the trace is not the only thing carrying the signal here. The ground under the trace is carrying it.
The ground return.
It's got to have the return path. Yeah.
Yeah.
So if you change layers, you're interrupting the return path, and people didn't realize that's what was causing reflections and crosstalk. When you would have all these signals changing layers, and you think, why am I still getting terrible reflections and crosstalk and radiation, EMI, when I've put the ground planes and polygons all around. Sorry, my video keeps dipping out because I'm using my phone as a webcam and people keep sending messages.
Ah, is that what's going on?
And
okay.
Every time there's a notification, my video stops and then comes back again up. It's
you get a kitty
annoying.
cat. Yeah.
Anyway, so what they didn't realize back then in the 90s was that, and it wasn't until even as recent as 2008 that I started seeing scholarly articles about people actually maintaining signal integrity by experimenting with return path vias.
We used to split the ground planes. I mean, that's...
Oh, yeah, that got out of fashion when people realized...
Back in the 90s.
They actually made... Yeah, because applications engineers from semiconductor companies would write these app notes and say, well, you want to control the return path of an A to D converter so that on the digital side, none of the digital currents...
They don't share return current paths.
Well, they have different grounds, and you join them at a Kelvin point where there's likely to be no current transfer between them.
What'd you call that? I call it a common tie point, but what'd you call it? A covent?
A Kelvin connection.
Okay. Like the current.
Kelvin,
okay.
Kelvin point. Yeah. But it's but now it's the prevailing wisdom has trumped that, and we now just have one unbroken ground plane under everything, because Kelvin junction, Chris, thanks. That's another way of calling it. Yep.
So Chris had actually, I think it was him, asked about what resolution could we see on a RG cable. And I'll tell you that this top trace right here is only 6 inches of a PC board. And so I'm seeing about 1/10 of an inch, if not smaller.
Right, so on RG8, the velocity of propagation...
It'll be muddier.
It's, I don't recall, but the RG8 cables are probably faster velocity of propagation than a
They got a velocity factor of about 0.7 is my memory.
Yeah, because they have the dielectric in them is mostly air, usually.
Well, then you're using a TE mode of propagation, and I think that's just a little faster. If somebody knows, but it's a circular mode of propagation as opposed to that moving field.
Yeah. Ernest, Lewis, yeah, you heard Eric Bogerton's talk and redesigned the boards. Yep, a lot of people have done that. You're not alone. I've done that. I've redesigned. I've gone to PCB West and sat in a class with Rick Hartley, and we talked about these things, and I went back and redesigned a board.
Oh, yeah, yeah. You know, Rick did the storm scope, which if you fly, this is one of the first tools. It was the first radar that I knew of that fit in a dashboard of a plane like a Cessna. And I'll tell you, it saved lives. I know people that say, I'm here today because of the storm scope. So I told Rick that when I met him you saved lives, dude.
He would have been delighted to hear that. He is such a great... All these guys, Rick Hartley, Eric Bogerton, Lee Ritchie, are just wonderful dudes who... They're really the brains trust of this industry. They'll tell you everything they know. Yeah. And they're in this kind of mode where they're most of them are getting towards or have already at least partially retired, and their mission now is to teach all of the rest of us what they know, so the industry, carries on and gets better, which is pretty awesome, I think.
So my settling time is probably in the couple picoseconds. The ringing you saw was actually the PC board ringing. And the guy from Samtech called me out on this. The head of you know his name too. I've forgotten it, but he's on the forum that you and me visit, and He said, "Yeah, you got some resonance in your one connector," and he was referring to this settling time problem here. This is an artifact of the board, not the test equipment.
That's it was that Istvan Novak.
Yeah, well, no, it wasn't Istvan. It was, but he's from Samtech. Yeah.
I thought Istvan was at Samtech now as a chief scientist or something. But anyway, I'm probably wrong. Hopefully one day he'll join us on this show.
Yeah, if we
awesome.
can learn to make this stuff happen every week at the same time with the same quality, yeah, I'd be all for it.
Yeah.
We do know how to work computers, people. We do, but but programmers now, we used to have programmer beatings because our opinion back in the Commodore days was the hardware is fine. It must be the programmer's fault. And of course, we were wrong, but you know, being hardware engineers, we were rougher people.
Well,
the guy that did the disk drive for the 128 was 6'8", separated my shoulder in a brawl. Matter of fact, you can see it sticking out of my shirt there.
Oh wow, yeah.
Yeah.
I bet you.
That was 30 years ago, and I'm still can't sleep on that side.
Oh, Bill, I bet you had a mouth on you in your younger days.
No, I got quiet. If I ever got quiet, you knew something was going on. And my eyes would dilate. They said they went black, but what's happening is they were dilating. And yeah, I learned early on to shut your mouth when you get mad.
Oh.
Yeah, I'm one of those that calculates.
I'm still working on that. Yes.
Well, I'm talking about when I'm going nose to nose with somebody. Around the house, I'm a scream. Yeah.
Revenge is a dish best served cold, so they say.
Oh, don't tell my dog that. My dog gets more revenge on me than any animal ever has in life. If I'm missing something off my workbench, I go out and look in the yard.
And it's all chewed up.
Yeah, yeah. Oh, and he's chewed up hard drives. I mean, he knows no limit to the weight he can pick up and drag out into the yard. So, all right, we're coming up on the hour. What should we close with here?
Well, hopefully next week I can walk you through my latest design I've been working.
Yeah. And I didn't do the programmer either, but that was having issues of its own.
And we wanted to
and we could talk about this image
MPC.
Next week.
We could, yeah. You can actually generate that yourself using some open source software that.
I'd love to see it.
I'd
love to see you do it.
Shared, yeah, there was this guy, and I don't remember his name right now, but he shared a very interesting and novel way of calculating or doing 2D field solving like this, called ATLC, the Arbitrary Transmission Line Calculator, and you put a bitmap into it, so you can actually create a cross section of any shaped transmission line you like using a bitmap, and it'll actually using the capacitance. What we know about capacitance, it will.
Oh, somebody, yes, go ahead.
It'll divide the whole thing up into a grid of series parallel capacitances in the dielectric, and calculate the impedance that way using the capacitance formula, and it's pretty accurate. And
so it's not lump sum; it's actual LC.
It's a numerical method for solving an arbitrary impedance or the impedance of an arbitrary cross section of some kind of transmission line structure, and there's a newer version of that. Someone upgraded it to include the field lines, so you can see what the field lines would look like if you want to.
Right.
And you don't need that to design good boards. You just need to know how to design a strip line and then specify.
You know what I use this drawing for? Is to remind me that the magnetic field is circular, and to turn my near field probe at right angles to the trace instead of, or to turn it in line with the trace instead of at a right angle. And that's something we can talk about. The way to tell them, EM means electro and magnetic, and the magnetic ones are the ones that are circulate around the conductor, and the electro ones are the ones that bridge between the return path and the conductor.
Yep.
So oversimplified, but so somebody said they were watching the other live thing. They were waiting for it to start. So my apologies. We accidentally tried to start. I tried to start too, evidently, and so people were hanging on the wrong one. How many people? How many viewers are there right now?
Oh, I closed the YouTube.
Don't worry about it. It'll tell us later.
It'll tell us. I could open it again.
Well, nah, we're good. It's coming up. So, yeah, it was good talking with you again. No, 22. All right, so we had less than last week. That's probably my fault. But, guys, we want to be here Friday again next week. We've started scheduling them if you want to catch us.
Yeah.
If you have topics you want to ask, by all means, either... Oh, I'm Be Heard.
You can comment.
Yeah, go ahead.
Or email, yep.
I was going to say, I'm Bill with one L at c128.com or BeHeard, B-H-E-R-D at c128.com. Those are the easy ones.
Yeah.
So,
or just comment in the recording of this stream on YouTube. Just put comments below and ask questions and request topics, and we'll have fun with it.
We'll make graphics even, or steal them. And we'll steal them. All the good ones have been done anyways.
Next week, so Bill, maybe next week live we can actually show, the MCC, talk about what we're working on.
And you can see it's all buggered up. Yeah.
And
so I'll load the IDE right on here.
Yeah. And we'll show the ATLC or that calculator I mentioned that shows you it's called ATLC too. I mean, anyone can go download it and check it out.
So a friend of mine just asked, real quick, mine asked, Mike Fikes asked if I've looked at the wire on the C128 board, and I haven't, but what I have that I've shown other people's brand new C128 boards. So that'll give me the ability to look at one with a wire and one without a wire.
Yeah.
Without circuitry. And then I can look at it with circuitry.
Yeah, you better get on to constructing those so we can analyze them.
I'll never get there. But yes, I should. So, hey, it was great talking.
I've got some Z80s. I have the 128 used a different 6502. It was a MOS 80 something, right?
8510. It's a 6502 with a port built into it. For down at 0 page, and they used it originally as I/O port.
Is it possible to still get those chips?
No, I don't think so. MOS is long, yeah.
Well, I know, but surely I must be able to.
There's people that are doing FPGA towers. They're combining a 6502 and or even just dropping the standard cell 6502.
Yeah, do that, and then do the same thing as a SID emulator,
which is harder because it's got analog circuitry on it. But there's some really good SID emulators out there. But people like the part of SID that was unintentionally broken. It became the feature set of the SID. So if you change it, the music will sound different, even though it's supposed to sound better. So a lot of people didn't like it when we did a die shrink on the SID. Oh, somebody asked about an emulator for a 6510. I built one. I use, this will take a ribbon cable to my analyzer, but that's reprogrammable as a 6502, a 6510.
And that's an FPGA on there?
That's an FPGA on there, right.
Which one did you use? A Xilinx, Altera?
It's a Cyclone 5.
Altera Cyclone 5.
Altera, right. And then that board's got these little itty bitty translators so that it protects the 5 volts. Basically, This is a 5 volt tolerant tower, but it actually puts out 3.3 volts, but that's good enough for TTL. So I have one.
It's got to be over 2.8 and you're good.
Yeah.
Well, 2.1 actually. It's 2.1 is the
2.4.
Something like that. Yeah.
Yeah.
Going back, that circles back to our
VIL 0.4 to 0.8. Yeah, I remember all that junk. I lived and died by it. So, all right, Ben, my friend. I think that does it for now.
Yep.
And we will see everybody here next week. Ben, you and I will hook up earlier, so we get our testing out of the way.
Yep.
So I'll try and catch around 1:30 at least.
Very cool.
Very good. Everybody have a good and safe